Chances are that you've come across the ChatGPT moment of robotics, the so-called Gemini Robotics 1.5 from Google DeepMind. Well, if you've missed it, or perhaps you want to learn a bit more, how does it work, why it works, and should you really care about it, or perhaps this is just another marketing fluke. So we'll be discussing this today in this 10 to 15-minute video. And for those who've come here the very first time, my name is Hassan, and wish you a very warm welcome from a very cloudy day in Eskişehir. It's called the Venice of Turkey. So it's very good to be here with you. It's been a while, and now we can dive right in. So I'll share my screen, and then we can start the discussion. Perfect. So, what's the big picture? The picture is that there are two main innovations here. Number one, you have Gemini Robotics Embodied Reasoning 1.5. So, this is the latest version 1.5. And if you just come over here, let me open the pointer as well. So, you see, we have 2D pointing, which is what is the exact location from the robot's perception. So, there's a camera mounted on a robot. From his point of view, from his egocentric vision, where is the center point of the pen holder, etc.? What is the trajectory? So if I want to take this red pen and I want to put it into the pen holder, how should the trajectory be such that I'm able to land the pen here? Of course, this has to conform to the laws of physics. And that's what we see over here is being done accurately. Then you also have state estimation. So this here is the glass holder, glass case, and right now it is open. So that's what written over here. Open, close. So if the laptop is open, it will say laptop open. Then you have segmentation mask, which is the exact sort of segmentation or mask over the exact shape. And it also, highlights the corresponding title of it. So this is a red pen, for example. Then you have object detection. So that's a bounded box. This is like a box which is more broader than a mask, which is the exact shape of the item. And then you have task progress prediction. So so let's say you're performing a task over 20 seconds or 30 minutes or whatever. How close are you towards achieving your objective? So you see over here, we were very close, but not quite done. There was some error, and then we are sort of progress dropped down to 0 almost, and then we started again. So that's error recovery. And then we start in this way. So why should we care about this? Well, if you want a robot to do long horizon tasks, which are complex, which requires it to interact with the environment, conform to physical laws, understand how far or close it to completing its task. So that's where GRER, ER stands for embodied reasoning, come into place. Now, this is powered by speech, text, images, and this is the visual language model. Now, it doesn't stop there. It also has access to tools. So maybe you guys, I hope, if that you are aware that frontier models like ChatGPT 5, Gemini, etc., they can access some coding environment. They can write codes, execute, and just give the result back to you. They can also use or call APIs to interact with the external environment. So let's say you wanted your robot to, let's say I have a humanoid robot and I wanted to automatically look into my schedule of the day and then do tasks such as laundry, cooking food, maybe folding my clothes, etc. So then it will go through my calendar. How will it do that? It'll access it through, let's say, Google API. It will read it, then it will reason across it. So, if let's say I'll be going to the office early in the morning, so maybe it needs to prepare breakfast for me. Once I'm there, then it can start doing the laundry, so on and so forth. You get the idea. So not only interacting and having these 6 things, but also access to this external environment, external knowledge. Maybe it doesn't know about something. It can go out there, do a research, like a deep research or a normal, Google or perplexity research, if you're divided and into that. And then secondly, you have Gemini Robotics. So this is the usual visual language action model. So it will take in your instructions, your images, and the robot sort of relevant inputs, let's say. And based on that, it will tell or ask the robot to take a particular action. So based on the environment, do X, Y, Z. And okay, cool. So big picture is there are two innovations, GRER 1.5, which is embodied reasoning, all the fancy stuff, and the typical VLA thinking traces. So you take what's the next step? Prediction to what do you require to accomplish the next task, and you describe it in a motion, which is a low level motion trajectory, so on and so forth. Now, why should we care about this? Well, GR 1.5, why is that important? Because normally, if let's say you have three robots, Aloha to Biarm Franca, Apollo, you would have to create a separate model for each of these. Why is this such a big issue? Why is this a pain point? Because A, uh, for each of these, you need to manually create the data. So you'll have an operator who will be performing different actions and you'll be collecting the sensor values for each action. So that will be your data, which is very hard to do, very expensive to do. The second option is creating it into a sort of simulation environment, something players like NVIDIA are trying to do. But regardless, this approach is not scalable or perhaps not reliable enough. So what if you could take the data from all three robots and use a single checkpoint, a single model that could operate on all three of these? So what does that mean? It means GR 1.5 can control different robot embodiments or three different robots which have different configurations with a single model to accomplish a variety of tasks out of the box. So the model was never trained on this. You give it a new task and it will still be able to perform. So let me give you an example over here. So this is by Franca. This is what the model was trained on. And then you have Aloha, and it's able to perform the task in a zero-shot basis. That means no further example or training was provided. Just right off the bat, it performs really well, so on and so forth. Cool. So next up, it is also able to perform reasoning when performing the task. And this allows it to handle complex tasks which require to be broken down. So GRV 1.5, why should you care? Well, instead of having one training a model for each robot, now you can get the entire world's data from all the research institutions, all the industry partners, something we did when you talk about computer vision, NLP fields. Now that thing is being done to robotics, where the biggest pain point is data scarcity. So this is a big unlock. More the data, more compute you throw at it, the higher likely this thing will work. We've seen it happen with ChatGPT, Gemini. Hopefully, we'll see it here as well. I mean, we have actually. The second thing, you integrate reasoning. So this is something all frontier models like Gemini, GPT, etc. have, and that allows it to perform tasks and get performance gains from there. Cool. So the next two slides, I'll try to be a little bit slow, and then we'll just, brush through the results. So this is Gemini Robotics embodied reasoning. We've already discussed about this. You have state estimations, glass case open, close, pen holders, object detection. Then you have pointing, what is the location of the object. You have trajectory prediction, progress understanding, segmentation masks, etc. Now, over here, you can see some examples in the real world. For example, you had a humanoid robot, some kind of robot, and you wanted it to go from here to there. What would it need to do to arrive there? Collision free. Then you also have a case of there's a waterfall. Let's identify 8 points that show the way the water is flowing. This is how that would be. Then you have a payload. So your robot is a physical structure. It can hold up to a certain amount of weight. So you want it to understand that. So it takes a look at these images and it says which parts or dumbbells am I allowed to pick up. Then you have very fine localization. So 10 points on the rim of the bowl. This is what that is. Then you can also use it to solve a task like matching all socks and labeling them based on their pattern. So, if the robots are able to do this, I'll buy them on day one because I don't know where my socks go at. And then you have point to the empty sockets. So, if you're lazy, you don't want to put your cell phone on charge, you can get your robot to do that now because they're able to do this. Cool. So those are some different various examples in different contexts. And how is this working, right? So to understand that, let us consider a user instruction. So I've taken this from all the images, the text from the official paper and try to give it to you in chunk size forms. Mind you, the actual paper was released 5 days ago, so I really hope this helps. I couldn't find something, so while I was studying, and I thought, why not share it with everyone else? So case in point, you have a travel itinerary, you look into the weather forecast. So the task is pack the suitcase for a trip to London. And now GRER 1.5 says, okay, where will you go? Let me look at the weather. And of course, you have security protocols built in, user permission, etc. And then it produces a high-level plan consisting of instructions such as pack the rain jacket into the luggage, that it communicates to the action model. Remember VLA, Visual Language Action Model, and then it decomposes those into shorter segments. So you can't give the entire thing to your robot in one go. It'll just not work. So you have to give it in small chunks or shorter segments to a few seconds for the robot movement, blah, 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 blah. So this thing dramatically improves the ability to handle multi-step tasks over a long-term horizon. Now, let's talk about results. And I'll try to be quick over here. So in this image over here, what's going on? So you have Gemini Robotics 1.5, which is the new one. You have the old robotics, Gemini Robotics, and you have this one, Gemini Robotics on device. I'm not quite sure about the less compute or decreasing performance. Maybe that's true, maybe not. I haven't studied it completely, to be honest. But what's the message? The message is, as you can expect, the recent innovation is perfect. It's better than the previous one. So look at this blue one. It always scores higher, but scores higher on what? So you have in distribution tasks. So this is tasks that are similar to training data. And of course, we expect peak performance. But what about out of distribution data? Something the model has not seen, it's new. So it can be so one dimension would be instruct generalization, ability to understand the intent behind natural language, including handling paraphrasing, typos, different languages, varying level of specificity. So we see GR 1.5 performs well for robot 1, it performs well for robot 2, and it performs well for robot 3 as well. Cool. Then we have action generalization, ability to adapt learned movements or synthesize novel ones. So you know some primitive movements, and now you combine them and to handle new initial conditions or object instances. Again, same story. GR 1.5 is better. Then you have something called visual generalization, which is what is the impact of lighting, something in the background on the performance. Again, we see that the performance of GR 1.5 is good. You can stop the video whenever you want and go down into more detail into each of these graphs. So what's the message? The message is if you're trying to perform a particular task, you have to, visual, action, instruction across all of three. If you're able to generalize, then you should be able to, theoretically speaking, perform that task. So this is, the golden benchmark. And we see again, GR 1.5 scores well. So let's be more specific. So the on-device version scores 0.41. The old GR scores 0.44, and this one scores 0.7. So, not bad. It's a very good performance jump and substantial gains we observe. So, big kudos to the team. Next up, we have this idea about multi-view success detection. So sometimes maybe the thing that you're trying to do is not achievable using a single camera, and you might need to access, two cameras. So this is, four different vantage points or perspectives, and the model should be able to, interlink or establish a correlation between all of them to perform a task. So in this case over here, did the robot successfully move the orange pack of biscuits from the basket onto the shelf next door? So this is the biscuit, and it was here before. And this is the close-up version. So this is the close-up version of the shelf. As you can see, previously it was like this, now it's like this. This is the close-up of this box over here. So I hope you get the idea. Yani, multi-view, it's able to do. And now let's talk about, more macro level what's going on. So again, instruction, generalization, action, visual, task. But how does it change based on single view, multi-view? So we see single view for action, it's 0.31, then multi-view is 0.39. So clearly we can see there is a benefit here. But sometimes it may not translate to task generalization. So it varies, based on that. So what's the key here? The key here is, let's say you also want to have an additional algorithm. So this was not shared. I didn't find any detail on it on the research paper. Maybe there's a separate paper for this, or maybe it was never shared. So there's something called motion transfer algorithm. All right. So in order to truly understand the multi-view system, this multi-perspective, you need a special algorithm to train the Gemini model. And that's the blue one. So when you look at the blue thing, now suddenly it starts performing really well across the board. And that goes on to say two things. Number one, multi-view, this thing you saw over here is beneficial, but to truly extract value from it, you need a special kind of algorithm, motion transfer. Now, I'm not sure how much time I've been speaking for, so I'll try to wrap this up quickly. So here's some more evidence on why you should care about this. So you have Gemini Robotics, the normal version. You give it something, and it's like gives you the single response. But you can get more gains by making it think. So it will give a response, introspect. Then it will give a response, and then it will reason again. It will again give a response, and it will think again. So this thinking on something we have seen in ChatGPT, Gemini, etc. So this is very critical. It just allows you to extract more value from frontier models. And you see that for Aloha, we have the biggest gains, but for other reward types, it may not be the case. But across the board, performance is better. If it wasn't obvious what VLA is, so it's taking visual language, which may also include text and audio. I mean, it does include text, but anyways, you get the gist, and then it will translate that into an action. Cool. Next up, we have the following. So we are training Gemini Robotics on Gemini model. So this is the general model which performs really well on mathematics, physics, blah, blah, blah. But we also want it to now excel in embodied reasoning. So something that we care about in robotics, that we want our robot to have, but it should also have the good things of Gemini, right? So we see that GRER 1.5 is able to accomplish that with thinking on, without off. So this is its performance. Long story short, you should care because you have a living, breathing Gemini thing in your room which you can talk to, and you don't need to use your laptop or your mobile phone. So the form factor is changing, right? And I think in many ways this is influential because this is a hard thing to do, right? Handling the physical world challenges and also keep retaining those general things. So this is quite impressive, if I'm being honest. Okay, and what's over here? we've already gone through it. The only difference is previously we were talking about, if I can. Okay, so we're drawing a parallel between robotics on device as well. But again, as you can expect, GR 1.5 is the best, not only for progressing towards the task, but also actually completing the task, which is may not be true for the other, let's say, types or versions of the models. Now, another closer look into this is you have progress understanding. Over here, the task is completed, so it goes to 100. But as you can see from here to here, there was a dip. That means there was an error, and now we have to restart and go back up, etc., etc. Multi-view success detection, we've talked about it. Now, this is important. Frame unshuffling. Now, we what the authors did is they shuffled the frames, and within the frames you have an image of a robot folding some clothes, and you want to unshuffle this. What to do this, we need to, the model should have temporal understanding. What is the appropriate logical sequence of steps? And we see the model is accurately able to do that. So this is the original piece of cloth. You start rolling it up, step 3, and then it's finally done. So you see, if the model is able to do this, it's able to understand, temporal logic. Now imagine you're in your house, and you want the model to remember that maybe in room 1, I always forget where my cell phone is at, and let's say I'm wearing smart glasses. It would be very nice for it to understand where my phone is in the house, or maybe it can you maybe connect to Apple and find the exact location and guide me to it. And case in point, that's option A, but if it can register within its memory where my phone is at, where are my belongings, my keys, I should be able to tell it, Gemini, please track my keys and let me know whenever I come, try to exit the home, remind me where my keys are at so that I can pick them up. So that temporal understanding of a long-term horizon, that's pretty, important, very powerful in real-world applications. So we're nearing conclusion. Of course, yet more quantitative evidence why GR 1.5, is groundbreaking, revolutionary, which it is. But this is a research paper, so we expect such things. Again, here we are trying to do two things. We are trying to compare online and offline. So right off the bat, online means real time, you know, 1 second, 5 seconds, 1 minute, whatever, you're doing it there. But offline means you're giving the model more time to think, more time to reason. Now, if the more larger the model, the more time it requires. But then again, there's always this thing going on where you're trying to optimize the model, you're trying to shrink it, but still retain its thing. But at all times, in the current situation, don't hold me to it 5 years later, is what I'm trying to say. As we stand today, offline is better because you have more inference time, you can think more. And let me show you over here, real-time multi-view and single view. Again, we're talking about that concept. So 0.66 goes to 0.74 and 0.59 goes to 0.79. So offline is better. Now let's talk about multi-view. So single view was 0.59, that goes to 0.66, meaning thereby multi-view is better. Cool. But you would notice that for offline, this is not observed. Interesting. Why did that happen? I'm not quite sure, but you get the idea. Because most of our applications which we really want will be real time. So let's just focus on this bit. That just gives you some perspective. But again, an important research area. I'm not quite sure why that happened over there. So they also compare it against GPT-5 mini, GPT-5. These things are always changing, so they've dated it that we access these using the API on a particular date. Blah blah blah. Cool. Now we can talk about the real world testing. So you have the academic benchmarks, and then you have industry partners who can actually put your thing to the test. So that's what has been tried over here. So if you have a shelf like this, the model is able to basically describe, okay, on shelf this, you have this, On this, you have this. This one is empty. This one has a large change back. Don't worry, I also can't read it, but you get the idea. Just go to the original paper at figure 14 and you'll get the hint. Again, best performance, but it's like 40, which isn't earth-shattering, but again, better than the previous one. So you see this incremental and hopefully exponential progress, meaning thereby this ChatGPT moment of robotics is more sooner than we think, hopefully. Okay, so just 2 slides left. Bear with me. Thinking, I hope that rings a bell. Again, this is about reasoning it out. So if the robot sees something like this, a gauge, so it will identify first its key features. For example, the markings of 30, 50, blah, 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 up to 250. Nice. So I thought the exact same thing. Then read the pointer position. So then I was trying to understand where is this pointer at. So I was like, so I thought, okay, it's between 50 and 80. And then what go through a process to understand, okay, it has to be 60. So much like a human, I saw a similar logic over there, which by the end of the day, it is trained on a human logic. It makes sense for this thing to occur. But imagine something that never gets tired, is always sharp. So that's what we observe over here. So these are select model thoughts, internal thought process, and this is the model response output. We can argue the same thing for the sock situation. We've already talked about it, so no need to spend more time there. Next up, we have the following. So this graph is very important because it allows you to understand that as you increase the thought token budget, how is the performance changing? So if you have an image, this orange line over here, and you have a video, which is this blue line over here, then you would understand that the performance is this green line, this one. Then you see, as you increase the tokens, the performance improves, which is good. You give it more time to think. But the same cannot be said about pointing. So it more or less, stabilizes there, but it's much lesser than the impact on image and video, as you can see. What is pointing, if you forget, it's that this dot over here, which localizes the location of the sock. And on average, this is the curve you see. So it goes from 58.2 and then 64.9. So that's how the performance changes. Inference time compute impacts performance. Then, we also notice that at some point, the output tokens, the tokens outputted from the model, despite this huge thought token budget, they stabilize around here. So after 2048, that's, they keep on staying at 980 output tokens. Then finally, you have the final graph, which is a comparison between Gemini 2.5 Flash and AR. You see a 6.6% difference between the two as you increase the thought token budget at its max point, meaning this model is able to truly exploit the benefits from more reasoning capabilities. So you can't just throw more compute or more money at the problem. No, the tech has to be right for it to make the most out of it. And finally, last slide, please bear with me. Okay, so what's the impact on everyday life? Well, GR 1.5, the final thing, which is a combination of 1.5 embodied reasoning, 1.5 VLA, VLM, blah, blah, blah. The final system, it allows you to perform something like blocks and drawer tasks, desk organization, sorting trash, packing suitcases, arranging objects, nut allergy, swapping things, mushroom risotto, blah, blah, blah. Now, as you can imagine, just Gemini robotics with thinking on, the results are not great across the board. So you stop the video and look at it, this blue one. But if you now use Gemini Robotics ER with this one, the performance goes to from 0.33 to 0.83, from 0.32 to 0.88, from 0.36 to 0.8, so on and so forth. Then you also have a comparison between Gemini 2.5 Flash and this one. So you see, it performs really well on blocks and drawer, but it fails at desk organization. The performance is not good for sort trash, packing suitcase, top shelf to the table. Good, more or less here, not good, not good. So the message is this thing, GR, GRER 1.5 and GR 1.5 from Google DeepMind. So this is something serious. You should take note of this. And big congratulations to the team for conducting this amazing research and putting it out there for everyone to read. And to all the technical and non-technical stakeholders, if you survived so far, please feel free to go through the report. It's very well written, very well documented, and I hope you find this videos useful. It's just been 5 days, so I've tried to just put something out there as soon as possible so you can truly understand and appreciate what's going on and what's our latest on in the robotics field. So thank you and have a good day. Bye bye.